All right, let's recap a little bit what we've been talking about in the last video. We have three kinds of elementary matrices: row swap, row multiplication, and row multiply and add. And we found in each one of those three cases, through exhaustive consideration, that the determinant of that matrix, that elementary matrix, multiplied by any matrix, is equal to the product of the determinant of the elementary matrix times the determinant of the matrix itself. Now, I just want to say that this is a particular interest of a very general type of expression that appears in mathematics. This is called operation preserving, and it's also called the homomorphism property. So I'm sure you'll see this in other places popping up. But again, if I multiply a matrix by an elementary matrix and take the determinant, that's the same thing as taking the determinant of M and the determinant of the elementary matrix. Now see, the right hand side here is simpler than the left, because if I have some matrix M, and then if I have a catalog of determinants of elementary matrices, I don't need to even perform the matrix product. I just multiply the determinants and I'm done. No need to do any matrix multiplication. So it simplifies things. Now what we want to do is take this one step farther. I can take any elementary matrix times a matrix and get the product. Now there's no reason why I can't repeat this process. Now we've just seen that the determinant of any elementary matrix times a matrix is equal to the determinant of E times the determinant of M. Now suppose I have this determinant of E1, E2, E3 times M. Well, this can be considered as the product of E1 times E2, E3M. And I can write that as determinant of E1 times determinant of E2, E3M. And now I can consider this one as the product of E2 times E3M. So that's going to be equal to, I'll leave this one the same, I'll just leave this as ditto. And then this becomes the determinant of E2 times determinant of E3M. And then I can just have here ditto determinant of E1 times determinant of E2, and then I can look at this one. This is determinant of E3, determinant of M. So altogether what I have is determinant of E1 times determinant of E2 times determinant of E3 times determinant of M. In other words, if I take any number of elementary matrices times a matrix and take the determinant of the result, all I need to do is take the products of the individual elementary matrices multiplied by the determinant of the original matrix. And that's what's expressed in this formula here. Well, not quite. We're going to apply this formula. Remember that the row echelon form of M is the product of elementary matrices times the matrix. So the writing is on the wall here. If I want the determinant of the REF, all I need to do is take the product of the determinants of the elementary matrices times the determinant of the original matrix. And so we write that down here. The determinant of the REF is the product of the determinants of each elementary matrix in the series times determinant of M. Okay? All right. Now the punchline is going to be that these determinants here are all non-zero. Okay? So the determinant here is 0 if and only if the determinant here is 0. Now, in what case is the determinant here equal to 0? Well, remember, if M is non-singular, then it row reduces to the identity. So in that case, certainly the determinant is not 0. if m is singular, then in fact there is some non-pivot column. If there's a non-pivot column, that means there must be a zero row. If there's a zero row in the REF, then the determinant 0. If the determinant here is 0, then the determinant here is 0. Okay. All right, so the bottom line is that determinant of REF is 0 if and only if m is non-singular. So that means the determinant of m is 0 if and only if m is non-singular or invertible. All right? All right, so that gives us m is invertible if and only if the determinant of m is not 0. Okay. Now, since the determinants of all the elementary matrices are not 0, that means they're invertible. And in fact, we've seen the inverses of these matrices. The inverse of a row swap is the same row swap. The inverse of a row multiplication is a row multiplication by the multiplicative inverse. And the inverse of a row multiply and add is a multiply and subtract. Okay. All right, now, one more thing. This is kind of the crown on the cake. Let's consider the product of two matrices. All right, now, each one of these has a REF, so we can write each one separately as a product of elementary matrices times its REF. Now, there's a little sleight of hand here. Originally we had that, well, let's write it here. Originally we had this. Originally we had that that REF of m is equal to E1, E2, up to E, I don't know how many, let's just say EK times m. Now we know each one of these e's is invertible. Okay. So what I could do is I could take this equation here and multiply both sides first by E1 inverse. Okay. If I multiply this by E1 inverse, and I multiply this by E1 inverse. Now I can do the same thing, but I have to multiply on the left on both sides. If I do this, then these two are going to go away, right? Then I multiply by E2 inverse. When I do that, I multiply here by E2 inverse, because this is already gone, and this one goes away. Multiply by E3 inverse, E4 inverse, etc. I can unpeel all of these e's and get m. So I can get that EK inverse, EK minus 1 inverse, all the way down to E1 inverse, times REF of m is equal to m. And these are all elementary matrices, and the only thing that I'm concerned is that they're elementary matrices, so that's why it's written here that we have m as a product of elementary matrices times its REF. And that's true for any matrix, so we write m that way, we write n that way. So let's consider the determinant of m times n. Well, m times n is not just m times n. M is this big product, n is this big product, so we're going to substitute this expression in for m and this expression in for n. Okay, so here's my m here, here's my n here. All right, and then I can take this determinant and break it out onto each one of these individual matrices. Okay. All right, now suppose that REF of m, suppose m is non-singular, then REF is m is the identity. All right. If REF is the identity, then I can then I can replace REF with I. And then in the first part here I have the determinants of the e's. The I is just there. Then I have the determinants of the f's, and then the REF of n. Okay. All right. So but the product of the determinant of e's is just the determinant of m. Okay. Bottom line is, if m is non-singular, then the determinant of m times n equals determinant of m times determinant of n. On the other hand, suppose m is singular. I can do the same thing. But instead of getting determinant of I, remember the REF of m, if m is singular, the determinant is 0. So the result will be 0. In other words, if the determinant of m is 0, the determinant of mn is also 0. So it still holds. Det mn equals det n times det n. All right, so we still have that true in both cases. And it's always true that the determinant of a product of square matrices is the product of the determinants, whether or not they're singular. Okay. All right.